Alright, this tutorial is going to be on running chi-square tests in SPSS. So there's actually two kinds of chi-square tests. There's a chi-square for goodness of fit, and then there's also a chi-square test for independence, which is also known as the Pearson's chi-square. So in both cases, with both chi-squares, we use a chi-square when we have categorical data, or in the language of SPSS, when we have group variables. So recall, a group variable is a variable where the values represent group membership or categories. So with the chi-square for goodness of fit, we're going to use that when we just have a single group variable, also known as a categorical variable. And what we want to know is whether the frequency of people having basically different values or belonging to different categories differs from the frequency of each of those categories that we would expect just due to chance or random sampling. So that's a chi-square for goodness of fit. The chi-square test for independence, otherwise known as the Pearson's chi-square, is used when we have two group variables or two categorical variables. And it's often used to determine whether there is an association or a relationship between those two variables. That's why it's called the chi-square test for independence. So it tells us whether the two variables are related or whether they're independent. All right, so let's get into it, and I'm going to use the same example that is used in the chapter. So in our example, we've got two variables. The first variable is the type of tree, and then the second variable is a variable called sound. And so this is kind of the silly example. What we want to know is, do people make a sound when trees fall on them? And more specifically, we're going to test whether or not there's a difference in the likelihood of people making a sound when a bamboo versus a redwood tree falls on them. So, silly example. One thing I'll point out is that the data for chi-square are often presented in a table format, often with tabulations. And so a good example would be to look at table 13.1 on page 200. And so what you've got on page 200 at table 13.1 is you've got something called a contingency table, where you've got the two different variables, and then the values of each variable make the rows and the columns. And so, for instance, if we're looking at table 13.1, we can look at the type of tree and then whether or not people made a sound. The data, when you enter the data in SPSS, we still need to have our two variables. Let's go to variable view. Okay. And then we need to have what you would say is the raw data rather than the summed data or the tallies, okay, or the overall counts. You need to have your two observations for each participant. So our first participant here, a bamboo tree fell on this person and the person made a sound. Okay, and so our first quite a few observations, these are all the people that had a bamboo tree fall on them and who made a sound. So our first 38 people, bamboo tree, they made a sound. And then starting at person 39, bamboo, but didn't make a sound. And then we can see redwood, yes, these people made a sound, all the way down to person 100, who had a redwood fall on them and they did not make a sound. Okay, so I point this out because what you're going to see for your lab assignment, I'm going to have you do the practice exercise at the back of the chapter, and they're going to start you essentially just with a table that basically has the overall counts, or kind of the summed counts. What you'll need to do is you'll need to take that table and you'll need to translate it into raw data. And so for this example, what I did is I just took the data on 13.1 and I said, okay, there was 38 people that had a bamboo tree fall on them and then they made a sound. So I just entered 38 observations of bamboo, yes. And then I also noticed in the table there was 7 people that had a bamboo tree land on them, but they said no. So then I entered those 7 people. So you'll have to do something similar with the table at the back of the chapter, where you're going to have to translate that summary table into the raw data for each participant. Okay, so in the variable view here, I just have a variable named tree type. I've labeled it, have had to enter values. I just did this in a way that was consistent with the textbook chapter. And then here we've got our values for whether they made a sound no or yes. So chi-square won't work unless you've got numerical values for each of your categories. So keep that in mind as well. All right, so the first type of test that we're going to do is the goodness of fit chi-square. And so this is going to allow us to determine whether the observed group frequencies for a single variable, just one of these variables at a time, differs from what is expected by chance alone. Now, a typical kind of starting place or test value or even null hypothesis, if you will, is that the expected values for each of the categories are the same. That is, for our tree type variable, we can test the hypothesis whether the actual values that we're observing among our 100 participants is the same or differs from the expected values that we would expect under the null hypothesis typically being that there's an equal number or an equal distribution of both of those values, both of those categories in the population. So essentially what we're going to test is to say, assuming that there is an equal number of bamboo trees and redwood trees, right, an equal 50% to 50% distribution, do we get that same 50-50 split in our sample? That's what we're going to test. Now, that's one version of a null hypothesis, that is that the categories are equal. As I'll show you, you don't necessarily have to have a null hypothesis that the categories are equal. And it is often the case when we use a chi-square in applied practice that we'll want to test whether the counts within each of our categories map on to kind of the expected percentages or proportions in a population. And so one application would be to say, okay, we've got a sample. Does the sample match the demographics in the population? One demographic variable could be race, ethnicity. Well, we know that there's majority groups and there's minority groups. We don't have an equal split or an equal representation among all groups kind of in society. So we want to say, knowing that those proportions aren't the same, do the proportions that we get in our sample match the proportions that we have in our population? So I'll show you kind of 2 different ways to test a null hypothesis. One would be that the categories are equal, and the other would be that we'll test our sample values against some starting values where we don't make the assumption necessarily that the categories are equal. So for our chi-square test of goodness of fit, we're going to go to our analyze menu, and then we're going to go all the way down to non-parametric tests. Non-parametric tests are those that don't make any assumptions really about what our variables kind of look like at a population level. Like they don't have to be normally distributed or anything like that. And then from non-parametric test, we're going to go into this menu that is called legacy dialogues. And then you'll see chi-square as the first option. So analyze, non-parametric tests, legacy dialogues, chi-square. How or why this is found in this menu, I'll never know, but this is where SPSS has it. So this is where our chi-square test for goodness of fit is. So we open up our dialog box for our chi-square test. So we've got our two different variables here. We've got type of tree and whether or not the person made a sound, and then our test variable list. So it's possible to do our two different chi-squares for goodness of fit on each of our variables separately. Okay, so we can move them over, and by moving both of our variables into our variable list, that will run a chi-square test for goodness of fit on each of those variables. Our next step is to make a decision, and we're going to decide whether the expected values for each group are equal or unequal. So here it's really just a matter of paying attention to what is the null hypothesis, what are we trying to test our sample against. Sometimes there's a null hypothesis that all categories should be equal, and sometimes there's a hypothesis that the values for the different categories are different and would match some kind of known proportions in the population. So our first test is going to be this basically this null hypothesis that all categories are equal. And so this would be testing the idea, like with type of tree, that there's an equal 50-50 split basically in the forest, and that there's some forest that is 50% redwoods and 50% bamboo, and does our sample match that? Okay, and so we can think that we've got 100 participants, and so if there's an equal 50-50 split of bamboo and redwood in the forest, then in our sample of 100 participants, we should have that same 50-50 split. In other words, we should have 50 bamboo trees and we should have 50 redwoods. Okay, so that's what we're going to test. Then what we actually observe, we'll test that against the 50-50 split. Same with make a sound. We're essentially having the null hypothesis that it's equally likely to make a sound versus not. There's some 50-50 split in the population as to whether people make a sound versus not when they get hit by a tree or when a tree lands on them. Such a weird example. All right. And then in our options tab, really, you can request descriptives, but they're not particularly meaningful when doing a chi-square. So we don't, I'm showing you this, but you don't have to do anything with your options tab. So when you've moved your variables over to the test list, and for this first test, it's all categories equal. That's all you need to do. Make sure to paste your syntax. I'm going to have you do that because you have to report your syntax for the lab. Okay? So let's go ahead and run that syntax. All right, so we've got a couple different tables. The first table that we get here, we can see in this first column, we've got the actual values that we're observing in our data. So this means that in our data, in our sample, there was actually 45 participants that had a bamboo tree land on them, and there were 55 participants that had a redwood tree land on them, and you can see that that totals up to the 100 participants that we have. Our second column is our expected n under the null hypothesis. Now recall that we had specified all categories equal. So basically what we're saying is of the 100 participants, we're expecting an equal 50-50 split. The residual is the difference between what is observed and what is expected. So in our first row, we see a residual of -5 because we had 5 fewer participants have a bamboo tree land on them than expected. Okay, so 45 minus 50 is a -5. For the second row, we have a residual of 5 because we had 5 more than expected participants have a redwood tree land on them versus what was expected. Same thing for our second variable, okay, with a similar interpretation. Is what we actually observed was that there was 47 people that did not make a sound. There was 53 people that did make a sound. Under the null hypothesis, both categories being equal, we would expect a 50-50 split. And what we've got here is an actual count. And the reason that it is 50 and that it's 50 is because we have 100 participants. If we had 50 participants, and we expected a 50-50 split, as in 50%, 50%, our categories would be 25 and 25. If we had 200 participants, and we expected a 50-50 split, we'd have 100 and 100. So the 50 and 50 represents actually the actual count or the actual frequency and not a percentage in this case. It only maps onto that 50-50 because we have 100 participants. Okay, and so the residual is then interpreted in the same way. So these are two variables with observed, expected, and then residual counts. I'm not going to go into the chi-square formula, but you should know that essentially the chi-square statistic, which is reported here, is based on kind of summing up the residuals. So as you might expect, if you get your observed frequencies and there's a good match for what was expected, the residuals are going to be very low and close to zero, in which case the chi-square statistic will be zero. Alternatively, if you have your observed frequencies that are very different from what was expected, we'll get large residuals, and when those residuals are basically counted or summed up, you'll get a larger chi-square statistic. The larger the chi-square statistic, the more likely it is that the observed frequencies differ in a meaningful way from what was expected ahead of time. Okay, so what we have here though, and then of course, that the size of the chi-square can be associated with a particular probability. And we do our tests of statistical significance in the same way, where what we're looking for is a significance value that is something less than 0.05. If we get a significance value that is less than 0.05, okay, we're looking at this bottom row of the table, we know that we have a statistically significant or meaningful difference between the frequencies that we actually observed and what was expected. If we don't have a statistically significant result, that is, if this significance value is something greater than 0.05, we do not have a meaningful difference between the observed frequencies and what was expected, okay? And meaningful difference is a key word there. Clearly, we have a difference between what we observed and what was expected, as in 45 is not 50 and 55 is not 50. So there is a difference. But what we should tell ourselves is that difference could happen just due to sampling error. In other words, in the population, you can still get this 50%, 50%, split. And in our sample, our sample can still be representative of that 50-50 split, even if we get 45 and 50, right? And this is a really good example to think about a coin flip, is that we could flip a coin and get 45 heads and 55 tails, and it can still be a fair coin, right? So what this is saying is that our sample frequencies do not differ. They don't depart in a meaningful way from this 50-50 split that was expected. And we know that because with our chi-square value of 1, that chi-square value of 1 does not happen less than 5% of the time, assuming that the null hypothesis is true. So we don't meet that threshold for statistical significance. Okay. Same thing with make a sound, yes or no. We have a chi-square statistic of 0.36 and our significance level of 0.549. Again, neither one is less than 0.05. And so the interpretation here is that we can conclude in both cases that the difference between the observed and the expected values is not significant. So with the first variable, with type of trees, we can conclude that bamboo and redwood are not significantly either overrepresented or underrepresented within our sample. Okay. Same thing is that in terms of people that either make a sound versus not, the people that make a sound versus not are not overrepresented or underrepresented based on the 50-50 split that we expected. All right. But now let's ask the question, what if we were actually somewhere where the ratio of trees in the forest was like 90% redwoods and 10% bamboo? And so we would expect in our sample, we should see a similar representation in our sample. That our sample should roughly reflect that same 90% redwood to 10% bamboo, okay? So then we could say, we have to kind of put on our, use our imagination, I guess, and we can say, okay, what if the numbers that we got in our sample, what if these were actually sampled from the forest in which it was 90% redwood and 10% bamboo? How likely versus unlikely would it be to get these numbers? Well, we can also test that null hypothesis. So let's go back, analyze, non-parametric tests, legacy dialogues, chi-square. What we're going to do here is, instead of having the default all categories equal, we're going to select the values option, and then we're going to add some values. So it's important here to remember what the values of our variable are. And recall that we had said that bamboo was 1 and that redwood was 2. So we know that basically bamboo comes first and redwood comes second. And that's important for specifying our values. So if we want to have 90% redwood and 10% bamboo, we know that bamboo is first. So we're going to enter that expected value first. All right. Now, what's the number that we need to put here? We kind of have to do a little bit of math, and we have to remind ourselves that there's 100 participants. And so our expected value is going to be 10% of 100. 10% of 100 is 10. Okay? So what we expect under the null hypothesis, if the forest is 90% redwoods and 10% bamboo, we expect that if we do basically a random sampling process, we should get 10 people that had a bamboo tree fall on them. Okay, alternatively, we expect that if it's 90% redwood, we randomly sample 100 people. We should have 90 people. 90 is 90% of 100. We should have 90 people that had a redwood fall on them. So these become our expected frequencies. I'm going to go ahead and paste that. There it is. Okay, so you can see the difference between the first analysis where expected is equal, and then the second analysis where expected is 10 and then 90. Okay, so let's go ahead and play that. All right. So oops, I still have my second variable in there. That's okay. Actually, you know what? It's not okay. Let's go ahead and take that out. We can just modify the syntax. I didn't want sound, so let's take that variable out. Play that. That's what we want to be looking at. Okay, so here's our expected frequencies under the null hypothesis, the 90-10 split. Okay, it's our same sample data. And so now what we're doing is we're looking at our residuals and we're saying, wow, we had 35 more bamboo trees than expected. We expected 10, we got 45. That's a residual of 35. Alternatively, we had 35 fewer redwoods than expected, basically under the null hypothesis. And so what we see is how that's reflected in the chi-square statistic. In this case, the chi-square is now very, very big, 136.11, because it's based on those very large residuals, or a very large difference between what we observed and what was expected. Our significance value is 0.000, telling us that the actual significance is something less than 0.001. So we know that this is a statistically significant difference. In this case, the observed values that we got for bamboo and redwood were significantly, substantially different from our expected values. Okay. And so you'll be asked to do kind of similar types of problems on your lab assignment, where you're going to test whether your observed frequencies, your observed distribution would be significantly depart from a null hypothesis in which the categories are assumed to be equal, and then from say a null distribution in which the categories are expected to be different from each other, but like a known kind of proportion. All right. All right, so now the next test that we're going to do, let's go back to our data. We're going to do a chi-square test for independence, otherwise known as a Pearson's chi-square. Very similar to a chi-square test for goodness of fit, the chi-square test for independence tells us whether a particular pattern of frequencies is likely due to chance or sampling error alone. It's different because instead of looking at a single variable at a time, we're going to evaluate the pattern from a combination of two different variables. And the other thing that this statistic tells us is whether or not there is a relationship between two variables. That is, if the two variables tend to be related or associated with one another, or whether they're independent. Another statistic that we're going to produce from this analysis is something called a phi coefficient, or it's also called Kramer's V. And this is going to be interpreted in much the same way as a correlation coefficient. So you can think of a phi or a Kramer's V, those are two different things, as telling us whether there is a correlation between two categorical variables. All right, so in this example, what we're going to try to determine is there a relationship between the type of tree that falls on you and whether or not you make a sound? Okay, so this analysis is going to tell us, is there some relationship or some association between the type of tree that falls on you and whether or not you make a sound? Maybe it's the case that if a redwood falls on you, you don't make a sound at all because you get squished. Alternatively, it's like maybe if the bamboo falls on you, it's very light, and so you don't really make a sound because you're like, okay, well, that didn't hurt so much. Or alternatively, it's like maybe the bamboo hurts for whatever reason and the redwood does. I don't know. We're just going to see, is there some correspondence there? Or are you equally likely to make a sound versus not, and it doesn't matter what the tree type is? Okay? So essentially the null hypothesis is there's no relationship and it doesn't matter what type of tree falls on you. You're equally likely to make a sound regardless of the type of tree. The alternative hypothesis is that tree type matters. You could say that there is some relationship or correspondence between the type of tree and whether or not somebody makes a sound. So here's how we analyze that. Now, it's a little bit unfortunate that this is the way that SPSS does things, but the chi-square test for goodness of fit and the chi-square test for independence are located in different drop-down menus. We're still going to go to Analyze, but here, instead of going down to non-parametric tests, we're going to be up at our Descriptive Statistics menu, and then under Descriptive Statistics, you'll see that there's this crosstabs option. Okay, so select crosstabs. Again, that's Analyze, Descriptive Statistics, crosstabs. Okay. So here, we do need to include both variables. So we're going to decide what variable to put in our rows and which to put in our columns. It doesn't actually matter. It doesn't matter at all which one you select as your row variable and your column variable. I'm just going to match what the book did. They put sound in the row variable and they put tree type in the column variable. So that way you'll be looking at an output that is consistent with what is in the book. But I could have just reversed that. It doesn't matter at all, not one bit. All right. Now, there's several options. There's a lot of options, in fact, in this analysis, and so we'll have to select the right ones. So the first thing you're going to do is go into the Statistics menu, click on the Statistics button, and you need to request the chi-square. So you'll see that that's the first option in the upper left-hand corner in this particular dialog box. So click on Statistics and then select chi-square. The other statistic or statistics that we're going to select, you'll see phi and Kramer's V. Select that. And those are the two options that we need. So once you've selected chi-square and then phi and Kramer's v, there's all kinds of other options. When you get into an advanced stats class, you'll learn about all these things. But for right now, that's all we need to select. Click continue. Okay, the other option is we're going to go into this cells button, and this is going to determine what appears in the cells of our table. What we're going to make is basically a 2x2 table, 2 rows and 2 columns. And so what we're choosing now is the information that is going to appear in those columns. So what you're going to select is, by default, the observed counts or the observed frequencies will be selected. And so this will tell us, for instance, this is basically what this will produce by selecting the observed counts. This will produce the counts that appear on page 200, table 13.1. Okay, so this will give us our observed counts. We're also going to click on the expected counts. So this would be under the null hypothesis, assuming that basically there's no relationship between the two variables. What would be the expected frequencies in each column that we would expect? You can get all kinds of other information. You can get the row and column percentages. We're not going to request that. The only other thing that I want you to request is you'll see this option to request residuals. So I previously discussed the residuals. You've got the option to get unstandardized, standardized, and then adjusted standardized. You should select adjusted standardized. I'm going to go ahead and select unstandardized as well. I think it'll help to just see where the numbers comes from. We're going to get a lot of numbers in these cells, so it can be a little bit of an overload, but I think by selecting the unstandardized residuals, that would be helpful. Okay, and then that's it. That's all we need. We don't need to worry about the format, the style, or the bootstrap. So once you've selected all those options, go ahead and paste it. All right. Go to my syntax. There we go. Run that syntax. All right, so we get a lot of output. All right, so this first box of output that we get is really only used to see if there's missing data. So this is our case processing summary. It just says that of the 100 observations, there was 0 missing data. That's it. Okay, the second table is basically our cross tabs or our cross tabulation. That's why there's this cross tabs menu. Essentially what's being reported are the tabulations or the counts for each group of one variable that's separated across the groups of the second variable. So what we can see with our observed frequencies, so count is our observed frequencies, we're getting the number of people that had a bamboo tree fall on them that didn't make a sound, okay? Or we're getting the number of people that had a redwood tree fall on them that didn't make a sound. And again, it's this 7 and 38 and 40 and 15 that will match the data that is found on page, flipping through my book right here, on page 200, table 13.1. May or may not be in exactly the right order of like rows versus, like the rows might not be exactly the same, but the number should match. Okay, so our count is our observed frequency, okay? The number of people actually in our data that had those values, okay? That, again, had a bamboo tree land on them and said no. In our totals, these will match our totals that we did with our goodness of fit. So recall that when we did our goodness of fit, we had 45 bamboo and 55 redwood. So we see those totals there. What we're getting here is the additional detail of how those totals are split by the second variable, which is whether or not people made a sound. So again, here we've got our totals, 47 and 53, which match our goodness of fit. And so you can just kind of think of this as providing more detail, is among the 45 people that had a bamboo tree fall on them, what was the split or the breakdown of people that either did not make a sound or did make a sound? Okay, the Next thing to look for in the cell is the expected count. Okay, so our expected count is basically what we would expect under the null hypothesis, is that if there is not a relationship between type of tree and making a sound, this is what we would expect based on the overall counts, or kind of the overall proportions, right? So if we have basically 45% bamboo and 55% redwood, we're basically going to expect that similar breakdown. If there's no relationship, we're going to expect that similar kind of 45% to 55% among people that don't make a sound versus people that do make a sound. And so that's how we get our expected counts. This 21.2 and this 25.9 reflect that 45% to 55% ratio or breakdown. So in fact, if you take 45% of 47, that's how you get 21.2. And if you take 55% of 47, that's how you get 25.9 in a similar calculation, okay? So just know that the expected count reflects what we expect if the null hypothesis is true and there is no relationship between type of tree and making a sound. What we expect then is roughly the same proportionality at kind of both levels of one variable versus the other, right? Is that we expect if overall we've got 45 to 55 bamboo to redwood, we expect that same breakdown or that same proportionality among people that either do or do not make a sound. So then what the chi-square test for independence does is it looks at the residuals, and that's why I requested the residual as well. And we're going to look and see, well, to what extent do our observed counts, our observed frequency, match what was expected ahead of time. What we can see here is that we've got some big residuals. And so we've got a mismatch between what we observed and what we expected. All of those residuals go into the calculation of the chi-square. Here's our chi-square test. And what you're looking for is this top row in the table. So our Pearson chi-square is a value of 32.476, which is a statistically significant result. What does this tell us? It tells us that there is a significant relationship between type of tree and making a sound. But much like an analysis of variance, which is an overall or omnibus test, so is the chi-square. This value alone does not tell us kind of what the nature of the effect is. That's why we have to look at the residuals and the adjusted residuals. The adjusted residuals can kind of be interpreted like a z-score. We're looking for a number that is greater than plus or minus 1.96. That tells us whether or not there is a significant departure from what is expected. So let's take a look at bamboo and no. We expected 21.2 people to be in this category. What we actually got was 7. So we see a negative residual, which then results in a negative adjusted residual. I won't go into how this adjusted residual is calculated. It basically just takes the residual and adjusts it for the row and column totals. But it suffices to say that if this number is kind of more or less than 1.96, we've got a statistically significant deviation. So what we can see here from this negative residual is that there were many fewer than expected people that had a bamboo tree land on them that didn't make a sound. We expected more and we got less. So there was fewer people that said no if they had a bamboo tree land on them. And then the flip side of that is that there was more people than expected, because the residuals are positive, there was more people than expected that didn't make a sound, that did not make a sound if a redwood fell on them. Kind of weird, but again, maybe they just got squished and so they didn't make a sound. Although they had to be, I guess they're in the study. So we had to, I don't know, it doesn't make sense. It doesn't matter. Okay. Again, here we can kind of, the flip side is we can look at the residuals. There was many more people than expected that did make a sound if bamboo fell on them. And then there was many fewer people than expected that made a sound if redwood fell on them. So if you have a significant chi-square, you need to then go and look at your residuals to interpret the pattern. Last statistic I'll show you is this Kramer's V. Okay, this is technically a different statistic than the phi coefficient, but when we have a 2x2 contingency table, they'll be the same. This can be interpreted in the same way as a Pearson correlation coefficient, and that it tells you kind of the strength of the association between two variables. With correlation of 0.1 or negative 0.1 being weak, a correlation of 0.3 or negative 0.3 being moderate, and a correlation of 0.5 or negative 0.5 or anything above that being strong. So what this Kramer's V is telling us is that there is a strong association between the type of tree and whether or not people make a sound. You'll see that there's a negative sign and then a positive sign. That just goes to see how it's calculated. You can just look at the absolute value and interpret the kind of the overall magnitude of this relationship. So this is telling us that there is a strong association between the type of tree that lands on you and whether or not you make a sound. And it seems to be the case that the relationship is that you're more likely to make a sound if bamboo lands on you, and you're less likely to make a sound if a redwood falls on you. So that's the way that we would explain in this entire analysis. That's the way that that would be kind of our final conclusion, is that what can we say about the relationship between type of tree and making a sound? Well, based on our pattern of frequencies, it seems to be that people are more likely to make a sound if bamboo lands on them, and they're less likely to make a sound if redwood lands on them. And we can tell by doing the test that the pattern that we observed in our sample, it departs so much from what was expected, okay, under the assumption that these variables are not related, that they're independent. It departs from that pattern so much that then we make the conclusion like, yeah, they just have to be related. You wouldn't get this pattern. It would be a low likelihood, it would be a low probability of getting this pattern if the variables were not related. Hence, they must be related. And the nature of that relationship is that you're more likely to make a sound if bamboo falls on you, and you're less likely to make a sound if the redwood falls on you. All right? So that's the interpretation. You'll be asked to do something similar on the lab assignment. And again, you're going to be given your data very much in kind of like an already tabulated format. So what you're going to have to do with your data is get it in this kind of raw format, and you're going to have to say, you're going to have to go to that, basically that table, and kind of recreate the data using this methodology. All right. Hopefully you found that helpful. Good luck with your lab assignments for this module.